This problem is different from the first problem, which only relied on friction to keep a car on going in a circle. In this case, we're going to go into a more realistic problem where a car is on a banked curve. And generally, roads are slightly banked when you turn, like off ramps from freeways are usually banked. So in this case, we're going to use banking in order to keep a car going in a circle around a track and not friction, since this is going to be a frictionless bank. The banking curve is 316 meters. The banking angle is 31 degrees. And the car needs to go into a circle. So what velocity would the car go into that circle without sliding up or down this frictionless ramp? We have two forces acting on it. We have gravitational force pointing down, and we have normal force pointing perpendicular to the top surface of the bank. We have our knowns right here. And I put mu of static friction to be 0, which includes mu of kinetic friction as well, but we don't need to put that. And we need to find the exact velocity for this car to remain steady on the ramp. So let's go ahead and start this off. We're going to say, we're going to figure out, first of all, which force is acting as a centripetal force. And it looks like gravity can't, because it's acting perpendicular to the centripetal direction. There's only one force or one component of this force that is acting parallel to the centripetal direction, and that is the x component of normal force. So we can say that normal force in the x direction is the centripetal force. Let's go ahead and write out the equation. So first of all, if the ramp is at 31 degrees, you can use logic to figure out that this angle here also has to be 31 degrees. That angle, if I were to just blow up the normal force vector, the angle here also has to be 31 degrees. This is the y component. This is the x component of normal force. So the x component will have to be looks like a cosine function of the normal force. So we're going to say that the x component of the normal force is the normal force times cosine of 31 degrees. And that's going to equal to, oh, I'm sorry, it's the sine component because it's opposite. And that's going to equal to centripetal force, which is just mv squared over r. All right, let's go ahead and just solve for v, assuming that we know everything, and we'll get this problem complete. V is then going to be r, normal force, sine 31, divided by m, all square rooted. Okay, so this is what we need to find out. This is everything else. We know what r is. We know sine 31, we know m, but we don't know normal force, f of n. So we're going to go ahead and do a little side quest. The side quest is to figure out what normal force is. What I'm going to use is the y component of normal force, and I'm going to go ahead and cancel it out with fg. And the reason why is because we know that if the car is going to stay on this ramp and we don't want it to slide, then the vertical position of the car is not going to change. So therefore, using Newton's second law in the y direction here, it's going to have to equal to 0. The sum of forces in the y have to equal to 0. So that being said, sum of all forces in the y equals to 0. That's going to be normal force in the y direction minus gravitational force is going to be 0. So normal force in the y direction is going to equal to gravitational force. Great. What is gravitational force but is mg? Cool. So now let's go ahead and take this apart a little bit more. What is normal force in the y direction? That's simply going to be a sine 31 component of normal force. So it's going to be normal force, cosine of 31. I get those two mixed up, I guess. So cosine of 31 times normal force is going to equal to mg. And therefore, normal force is going to equal to mg divided by cosine of 31. Perfect. So now we have a function for normal force. Let's go ahead and take that and plug it back into our original equation. So side quest is over. V is then equal to the square root of r, but now Fn is going to be this hunk of junk right here. It's going to be mg sine 31 on top divided by the m and then cosine 31 on the bottom. Okay, so I just replaced Fn with this. Again, m's cancel out, and v will finally be rg sine 31 divided by cosine 31. And we're running out of room here, but I think we can solve this out. This ends up being 43.136, et cetera, meters per second. And to get it in line with two significant figures, which 31 is the least number of significant figures of all that is given to us. So the velocity ends up just being 43 meters per second. And that is your answer. So without any friction, if this car were to go along this banked curve and the car is going in a circular loop that's vertical in this point of view, then the car can go 43 meters per second exactly in order to not slide down the ramp due to gravity or slide up the ramp due to centrifugal effects. Okay, so it's just for the car to remain on the ramp.